Hello there, and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath the stars. Tonight we're going to travel outward through every familiar layer of the cosmos and ask what would happen if we somehow reached the edge of the universe. At first the question seems wonderfully simple. A room has walls. A road eventually ends. A coastline gives way to water. So perhaps the universe also has a final border, a place beyond the last galaxy where space simply stops. We might picture a black surface hanging in the darkness, or a silent cliff beyond which there is no distance at all. But the universe does not appear to offer us that kind of edge. The boundary astronomers can meaningfully discuss is not a wall waiting in some remote location. It is a horizon created by the finite speed of light, the age of the cosmos, and the expansion of space. The farther we look, the further into the past we see, until distance itself becomes a record of earlier time. So our journey toward the edge will not lead to a final object. It will lead toward the limit of what information has been able to reach us. For a moment, begin much closer to home. You may be listening in a dark room, perhaps with a window nearby, while the night sky appears calm and almost flat above the roofs and trees. Yet every point of light arrives after a delay. Moonlight is already a little old when it reaches your eyes. Sunlight is older still. The stars are seen not as they are at this exact moment, but as they were when their light began crossing space toward Earth. Most of those delays are small compared with the age of the universe, but the principle is the same at every scale. Looking outward is always a form of looking backward. The sky is not a single picture of one cosmic present. It is a collection of messages sent at different times, arriving together in the quiet of your room. You do not need to remember every term we meet tonight. There is no examination waiting beyond the observable universe, which is fortunate, because the universe has shown very little interest in supplying convenient revision notes. It is enough to keep one simple image in mind. Every step outward carries us deeper into the past. Before we drift any farther, I'd love to know where in the world you're listening from tonight and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you liked the video and subscribed to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. And for tonight's question, if the universe really did have a physical edge, what would you imagine seeing on the other side? There is no correct answer required. A wall, another universe, perfect darkness, or perhaps something with the slightly disappointing appearance of an office corridor at closing time would all reveal something interesting about the way human imagination tries to give shape to the unknown. Now let your shoulders loosen a little, settle more comfortably into the pillow, and allow the room around you to become quieter. You do not need to hold on to every distance or definition. Let the details pass gently, knowing that the journey will continue even if your attention wanders. We can move slowly. Where do the galaxies finally stop? Is the most distant light also the farthest place? Why can we see only part of the universe if space may continue beyond it? Would a traveller moving fast enough ever catch the horizon? Does every observer have a different edge? And can something truly have a boundary when there is no wall, no surface, and perhaps no outside? These questions sound separate at first, but they all lead toward one distinction. The universe itself and the universe we can observe are not necessarily the same thing. To begin that distinction, imagine standing in a wide open landscape on a clear day. In every direction, the ground appears to meet the sky along a distant line. That line looks like an edge. It surrounds you, and you seem to stand at its center. Yet you know the land does not end there. If you walk toward the horizon, it moves with you. Another person standing many kilometers away sees a different horizon centered on their own position. The horizon is real as a limit of vision, but it is not a physical fence built into the landscape. The edge of the observable universe is similar in one important way. It marks a limit to what can currently send information to us. But the comparison soon reaches its limit. A landscape horizon exists because Earth is curved and your view is blocked by the surface. A cosmic horizon arises from the history of light traveling through an expanding universe. There is no hill hiding the rest. There is only space-time distance, and the finite time available for signals to arrive. This means the phrase edge of the universe quietly combines two very different questions. One asks about the total universe, whether all of space is finite or infinite, whether it curves back on itself, and whether it has any global form we could describe. Science does not yet provide a complete answer. The other asks about the observable universe, the region from which light or other information has had enough time to reach us. That region does have a meaningful limit, but it is centered on the observer and shaped by cosmic history. It does not prove that Earth occupies a special position. An observer in a distant galaxy would also see an observable region centered on themselves, overlapping ours in some places, and extending into regions hidden from us in others. So the first answer to our title is gentle but decisive. If you travelled outward, you would not expect to find a wall marking the end of existence. You would move through structures, emptier regions, older light and changing horizons, while the supposed destination kept becoming a question about time rather than place. Before we can understand that horizon, though, we must first leave the familiar scales behind and watch the ordinary landmarks of the cosmos slowly disappear. The familiar universe disappears in stages. First the room falls away, then the city lights, then the curve of Earth, until our planet becomes a blue sphere suspended in sunlight. From this distance, every border drawn on a map has vanished. Oceans, continents, clouds, and night move across one shared world, while the moon follows its patient path nearby. Even here our sense of scale is already beginning to loosen. The distance between Earth and the Moon is large enough to fit every other planet in the solar system between them with some room remaining. Yet in astronomical terms the Moon is still close. Light crosses that gap in a little over a second. A radio message can travel there and return while a conversation is still waiting for its next sentence. The edge of the universe, whatever that phrase may eventually mean, will not reveal itself at any distance our instincts were built to understand. We must begin by allowing the first familiar measures to become small. Moving farther outward, Earth and the Moon shrink into a close pair of lights, and the Sun becomes the dominant object. Sunlight takes a little over 8 minutes to reach Earth, carrying the warmth of a star about 150 million kilometers away. That distance defines one astronomical unit, a convenient measuring stick for the inner solar system. Mars orbits farther out. Jupiter circles beyond it. Saturn, Uranus, and Neptune occupy paths so large that diagrams usually compress the empty spaces between them. Otherwise, the planets would become tiny marks separated by inconvenient amounts of blank paper. Beyond Neptune lie icy worlds, scattered objects in the broad region of the Kuiper belt. Yet none of these forms a final border. The solar system has several possible edges depending on whether we measure planets' solar wind or the reach of the Sun's gravity. Even before leaving our local neighbourhood, the universe has begun teaching the same lesson. Natural systems rarely provide one clean line simply because our maps would prefer it. Soon the Sun itself starts to resemble an ordinary star. From the outer solar system it is still brighter than anything else in the sky, but its warmth has weakened into a memory. The planets become almost impossible to see, lost in the Sun's glare, and the immensity surrounding them. Ahead lies interstellar space, where the nearest neighbouring star is more than 4 light-years away. A beam of light could circle Earth several times in a single second, yet it would need years to cross the distance between the Sun and its nearest stellar neighbours. Our fastest spacecraft would require thousands of years to make such a journey with current technology. The comparison is not meant to make the distance feel hopeless. It simply shows how quickly human speed becomes irrelevant. Rhodes aircraft and even planetary missions belong to one scale. The spaces between stars belong to another. From here, the solar system no longer looks like a grand arrangement of worlds. It looks like one faint household in a dark and widely scattered neighbourhood. As we continue, individual stars multiply until they form the Milky Way around us. Our galaxy contains hundreds of billions of stars arranged in a disk with spiral structure, a central bulge, and a much larger, fainter halo. From inside that disk we see the Milky Way as a pale band crossing the night sky, because we are looking through a great concentration of distant stars, dust and gas. Pull far enough away, and the band becomes a galaxy. A broad wheel of light roughly 100,000 light-years across, though its more diffuse components extend farther. The solar system occupies no central throne. It lies in a minor spiral feature far from the galactic centre, moving with countless other stars through a structure too large for any human civilization to explore on ordinary timescales. Still, the Milky Way is not the universe. Its apparent edge is merely the place where its stars become sparse, and its halo fades into intergalactic space. We have left one enormous structure only to discover that it was one object among many. Beyond the Milky Way, the Andromeda Galaxy and dozens of smaller galaxies belong to the local group, a gravitationally connected collection spread across millions of light-years. Farther out, galaxy groups gather into clusters, and clusters take their places within a much larger pattern. Galaxies are not scattered randomly like salt across a table. On the greatest observed scales, they trace filaments, sheets, knots, and vast low-density regions. Together these form the cosmic web. Its brighter concentrations can be imagined as cities connected by long roads, with enormous quieter landscapes between them. But even that analogy is too orderly. The web grew from tiny differences in the early distribution of matter, shaped over billions of years by gravity, dark matter, gas stars, and cosmic expansion. It has no planned centre and no outer ring visible from our position. Each time we cross what looks like a boundary, a larger pattern appears. Planetary system becomes galaxy. Galaxy becomes group. Group becomes filament. The map continues opening beneath us. Now let the entire nearby cosmic web begin to shrink. The Milky Way is no longer identifiable. The local group becomes one small concentration among countless others. Vast voids and luminous filaments form a delicate three-dimensional texture, extending in every direction we can observe. At this scale, asking where our home is becomes difficult to answer without moving inward through many nested layers. Yet nothing we have crossed has brought us closer to a physical edge. We have passed the boundaries of objects, not the boundary of space. The limits of planets, galaxies, clusters, and filaments are defined by matter, becoming thinner, gravity becoming weaker, or one structure giving way to another. They do not tell us where the universe ends. To search for that more elusive limit distance alone will not be enough. We must pay attention to the light arriving from each region, because every farther structure appears to us at an earlier moment. The next stage of the journey is not simply outward, it is backward. Distance in the universe is never only distance, it is also delay. As we continue outward from the fading structures of the nearby cosmic web, every object ahead sends us information at the same finite speed. Light may be extraordinarily fast, crossing nearly 300,000 kilometers of empty space in a second, but the universe is extraordinarily large, and it has had plenty of room to make even light seem patient. Nothing we see in the sky appears to us in a perfectly shared present. Every star cloud and galaxy is shown through a message that required time to arrive. The farther away the source, the older that message becomes. This is not a weakness in our telescopes, and it cannot be solved by building a larger mirror or a more sensitive camera. It is woven into the way cause and effect move through space. The universe does not deliver its news instantly. It sends everything by light gravity particles or other physical signals, and all of them must obey the causal structure of space-time. The delay is easy to overlook when we remain close to Earth. Light from the moon needs only a little more than 1 second to reach us, so when you look at its bright surface, you see it as it was just over a second ago. The difference is too small for ordinary experience to notice. Sunlight takes a little more than 8 minutes to cross the distance from the sun to Earth. The warm light resting on a wall this morning therefore began its journey several minutes before it entered your room. If the sun could somehow change at this instant, Earth would not receive any information about that change immediately. For those few minutes, the old sunlight would continue arriving, carrying an image of conditions that had already passed. This does not mean the sun is secretly living in the past. It means our knowledge of the sun is delayed. The distinction will become increasingly important as we move farther away, because soon the delay will no longer be measured in seconds or minutes. It will be measured in lifetimes. The nearest stars beyond the sun are more than 4 light-years away. Their light has travelled for more than 4 years before reaching Earth, so we see those stars as they were several years earlier. Most of the stars visible to the unaided eye are tens, hundreds, or occasionally thousands of light-years away. A star whose light began travelling during your childhood may only now be appearing above you. Another may be showing us a state from before any living person was born. We often speak casually about looking at a star as though sight creates an immediate connection between 2 present objects. In reality, the star sends light outward in every direction, and a tiny portion of that expanding radiation eventually enters a human eye. The process resembles receiving a letter from a distant traveller, except the envelope contains not a written description, but a physical trace of the sender's earlier condition. Its colour spectrum, brightness, and motion all carry information. The letter may be old, but it is remarkably detailed. The comparison with letters has a limit. A letter waits somewhere before being delivered while light does not pause between stars. It moves continuously through space, and the delay belongs to the journey itself. Nor does the light carry a complete picture of everything happening at its source. Astronomers must reconstruct the object from the information that arrives. They separate wavelengths, measure tiny shifts in spectral lines, track changes in brightness, and compare those observations with models of matter, gravity, and radiation. A point of light can reveal a star's temperature, chemical composition, movement, and sometimes the presence of orbiting planets. Yet all of those measurements describe an earlier version of the system. The telescope can improve the clarity of the message, but it cannot make the message younger. Astronomy is therefore a science practiced almost entirely through delayed evidence. The sky is less like a live window and more like an archive whose pages arrive continuously 1 photon at a time. At galactic distances, the archive becomes far older. The light we receive from the Andromeda galaxy has travelled for roughly 2.5 million years. We see that great neighbouring galaxy as it appeared long before modern humans built cities, wrote histories, or named the pattern of stars in which Andromeda appears. More distant galaxies are observed tens of millions, hundreds of millions, and billions of years in the past. a galaxy seen several billion light-years away may appear younger, smaller and less settled than nearby galaxies because we are observing it during an earlier period of cosmic history. We are not seeing a modern galaxy placed at an extreme distance. We are seeing an earlier universe. This is one reason deep astronomical images contain objects from many different ages at once. Nearby stars belong to the relatively recent past. Farther galaxies belong to older chapters. The deepest visible sources reveal periods when the first generations of galaxies were still assembling. One image can therefore hold an enormous stretch of time layered across the same dark field. This finite speed of information also protects the order of cause and effect. According to relativity, no locally transmitted message can outrun light in a vacuum. A massive spacecraft may move faster and faster, but it cannot be accelerated through that limit. The rule is not merely an inconvenient restriction placed on future engines. It helps define which events can influence one another. If a signal has not had enough time to cross the distance between two regions, those regions cannot yet have exchanged information. They may exist within the same universe while remaining outside one another's observable history. As we travel toward greater distances, we are therefore not approaching a wall made of matter. We are approaching the oldest messages that have had time to reach our location. Beyond some point, information has simply not arrived, and because every additional distance reveals an earlier moment, the universe ahead of us will soon stop looking like the universe we recognize. The outward journey is becoming a passage through earlier and earlier cosmic time into a universe made of many different moments. The deeper we look into space, the less the universe resembles a single moment. Nearby stars, distant galaxies, and the faintest structures visible to our telescopes do not appear together in one shared present. They arrive from different ages layered across the sky according to how long their light has travelled. This is one of the quietest and strangest consequences of astronomy. We may point one telescope toward one small patch of darkness, yet within that narrow field we can receive light that began its journey thousands, millions, and billions of years apart. The image appears flat on a screen, but its depth is also a form of time. Every more distant object belongs to an earlier chapter. If we could somehow move outward without limitation, we would not simply pass through greater amounts of space. We would encounter increasingly ancient versions of the cosmos. The journey would become less like crossing a landscape and more like walking backward through history, except there would be no neat doorway between one era and the next. Cosmologists describe this relationship using the idea of a past light cone. The name sounds more technical than the basic picture needs to be. Imagine your present moment as the narrow point of a cone. Every signal reaching you now must have travelled from somewhere inside the widening region behind that point. Nearby events had only a short distance to cross, so they occurred recently. More distant events needed more time, so they happened farther in the past. The farther back the cone extends, the larger the region from which light could have begun its journey toward you. This does not mean that the universe itself is shaped like a cone. The cone is a map of which events can influence one observer at one moment. It is a diagram of causal history. Your eye is a telescope, and every scientific instrument receives information only from events whose signals have had enough time to arrive. Everything outside that past light cone is not necessarily absent. It is simply unable to affect your present observation yet. To picture the layers more gently, imagine standing at the centre of a vast museum arranged in transparent shells. The nearest shell contains the recent universe planets, nearby stars and galaxies, seen only slightly earlier than their present condition. Beyond it lies another shell containing older light. Farther still, galaxies appear during earlier stages of their development. Continue outward, and the shells reveal a cosmos with fewer mature structures, more active star formation, and galaxies still gathering into the shapes we recognize today. The museum analogy is useful because every step outward opens an earlier room. But the real universe does not divide itself into polished galleries with dates written above the doors. The layers overlap continuously. Different directions contain different objects. Some nearby stars are older than distant young galaxies, and some remote light comes from processes that lasted across long periods. The shells are not physical surfaces. They are a way to organize arrival times. The universe remains three-dimensional, irregular, and wonderfully unwilling to arrange itself for convenient viewing. There is another subtle point. When we observe a distant galaxy as it was billions of years ago, that ancient appearance is not frozen permanently at the galaxy's location. The galaxy continued to evolve after emitting the light we now receive. Its stars aged. New stars may have formed. Some stars died. The galaxy may have merged with neighbors, changed shape, or fallen into a larger cluster. We simply do not yet see those later events, because their light is still traveling toward us. In that sense, a distant galaxy has several different meanings depending on the question being asked. There is the galaxy we observe in the past. There is the galaxy as it may exist today, inferred through models rather than directly seen. And there is the sequence of future images that may continue arriving over immense stretches of time. Astronomy rarely gives us the present state of a remote object. It gives us evidence from which the present must be reconstructed. The farther away the object lies, the greater the gap between observation and inference. As our imaginary journey continues, the appearance of the universe changes more dramatically. Nearby cosmic space is filled with large spiral and elliptical galaxies, clusters, and long filaments shaped over billions of years. At greater look-back times, the galaxies we observe often appear less settled. Their structures may be smaller, more irregular, and more actively forming stars. Travel deeper still, and we approach periods when the first generations of galaxies were assembling from gas drawn into growing concentrations of dark matter. The familiar cosmic web was present in younger form, its great pattern developing rather than complete. We should be careful not to imagine that every direction follows one identical visual sequence. Cosmic history is uneven. Some regions mature earlier than others, and observations are influenced by brightness, dust, wavelength, and the capabilities of our instruments. Still, the broad progression remains clear. Looking farther reveals an earlier universe, and an earlier universe looks different because it had not yet had enough time to build the structures surrounding us now. Eventually, this layered history reaches a point where ordinary galaxies can no longer guide us farther. Their light grows faint, their forms become difficult to resolve, and the universe we are observing becomes younger than the oldest known systems of stars. Beyond the era of the earliest galaxies lies a darker period before starlight had filled the cosmos, and beyond that darkness waits an even older signal not emitted by stars or planets, but released when the young universe itself became transparent enough for light to travel freely. That signal now surrounds us in every direction as a faint microwave glow. It is often pictured as a shell at the edge of the observable universe, but it is not a wall, and it is not the place where space ends. It is the oldest electromagnetic light currently available to us, carrying an image of the universe, before galaxies, before stars, and before the long architecture of the cosmic web had fully emerged. The next boundary in our journey is therefore not the last object in space. It is the oldest light in the sky. The oldest light in the sky does not come from the oldest stars. It comes from a time before any stars existed at all. As our journey moves beyond the earliest galaxies, the familiar sources of light begin to disappear. There are no spiral arms, no glowing nebulae, no planetary systems, and no steady points resembling the stars above your window. We are looking into a universe that is younger, hotter, denser, and far less structured than the one around us now. Yet this earlier cosmos is not completely hidden. A faint signal arrives from it in every direction, filling the sky so evenly that no ordinary human eye could notice it. Today that signal has been stretched into microwave wavelengths and cooled to only a few degrees above absolute zero. Astronomers call it the cosmic microwave background. It is not a collection of distant objects. It is a surviving field of ancient radiations, carrying an image of the universe when it was only about 380,000 years old. Before that light began travelling freely, the young universe was filled with a hot plasma of atomic nuclei, electrons and photons. Matter had not yet settled into the neutral atoms that would later form gas clouds, stars, planets, and eventually the materials around you. Free electrons interacted strongly with passing photons, scattering them again and again. Light could move, but it could not travel very far in one direction before being redirected. The universe was therefore opaque, not because it lacked light, but because it contained too many charged particles for light to cross it cleanly. Imagine trying to see through a thick, brilliantly illuminated fog. The brightness is present everywhere, yet no distant view can emerge because the light is repeatedly scattered before reaching you. The comparison is imperfect, as all cosmic household arrangements eventually become, but it captures the essential difficulty. The early universe was full of radiation and still impossible to see through. As cosmic expansion continued, the universe cooled. Eventually conditions became calm enough for electrons to remain bound to atomic nuclei, producing mostly neutral hydrogen and helium. This transition is often called recombination, although it was the first lasting combination of these particles rather than a reunion after an earlier domestic disagreement. Once most free electrons were no longer wandering through the plasma photons, could travel much farther without being scattered. The universe became transparent. Light that had previously been trapped in continual interactions began streaming through space, and some of those photons have continued travelling ever since. They cross our instruments today after an enormous cosmic journey greatly changed in wavelength but still carrying information about the matter from which they last scattered. The cosmic microwave background is therefore not light from one object or one explosion. It is the released glow of the young universe itself, observed at the moment when space became transparent enough to preserve a visible record. When astronomers map this radiation, they often display it as a coloured oval covered in tiny warm and cool variations. The colours are added to make differences visible. The actual radiation does not resemble a painted sky. Those slight temperature variations reveal small differences in the density of the early universe. Some regions contained a little more matter than others. Over billions of years, gravity amplified those differences, helping matter gather into the structures that would become galaxies, clusters, filaments, stars, and worlds. The microwave background is therefore not merely an ancient photograph. It contains the early pattern from which much of the later cosmic architecture grew. The variations are extremely small, yet their consequences became immense. A slightly denser region could attract more matter, becoming denser still, while emptier regions gradually developed into the great voids between filaments. The calm microwave glow around us carries the faint beginnings of nearly every large structure we've crossed on our outward journey. It is tempting to imagine this radiation as a physical shell surrounding Earth with the rest of the universe waiting behind it. Cosmologists sometimes use the phrase surface of last scattering, which can strengthen that picture. But there is no solid surface floating at one final distance. The surface is the collection of locations from which the photons reaching us today last scattered before beginning their long, mostly uninterrupted journey toward our present position. An observer in another galaxy would receive different photons and would define a different surface around themselves. As time passes, we receive light that began its free journey from slightly different regions. The boundary is part of our observational history, not a permanent shell built into space. It surrounds us in every direction, because wherever we look deeply enough, we eventually look back to the era when the universe became transparent. We're not standing at the center of a cosmic sphere. We're standing at the endpoint of the particular light paths reaching us now. Nor does the cosmic microwave background mark the beginning of the universe. Earlier periods existed, but ordinary electromagnetic light cannot show them to us directly, because the universe before recombination was opaque. Cosmologists investigate those earlier conditions through physical models, particle processes, patterns within the microwave background, and possible messengers other than light. The signal therefore represents both a remarkable view and a genuine limit. It is the earliest electromagnetic image currently available, but it is not the first moment of existence, the location of the Big Bang, or the outer edge of space. We've reached a boundary of visibility rather than a boundary of being, and one more puzzle now waits inside that boundary. The light has travelled for nearly the age of the universe, yet the matter that released it is now much farther away than a simple multiplication of time by the speed of light would suggest. To understand why, we must allow the space between source and observer to change while the light is crossing it. A universe almost 13.8 billion years old might seem capable of revealing a region no more than 13.8 billion light-years away. Light travels 1 light-year in 1 year, so the arithmetic appears pleasantly cooperative. Yet under the standard cosmological model, the present radius of the observable universe is roughly 46 billion light-years. Its full observable diameter is therefore around 93 billion light-years. Nothing has secretly allowed light to travel faster than light, and the universe has not misplaced several dozen billion years in its bookkeeping. The apparent contradiction comes from treating cosmic distance as though space remained unchanged while the light crossed it. It did not. During the billions of years that the oldest light travelled toward us, the universe expanded. The separation between distant, unbound regions grew, including the separation between us and the matter that released the light. The journey time tells us how long the signal has been travelling. It does not automatically tell us how far away its source would be measured today. Suppose a distant region released a photon toward the location that would eventually contain the Milky Way. The photon always moved locally at the speed of light. Any nearby observer along its path would measure exactly that familiar speed. Yet while the photon travelled, the large-scale distance between widely separated regions of the universe continued changing. One common analogy imagines a person walking toward you along a walkway that stretches while they move. The walker makes steady progress at every local step, but the total distance between the endpoints does not remain fixed. By the time the traveller arrives, the place where the journey began may be far more distant than the original path length. This helps explain why ancient light can have travelled for nearly the age of the universe, even though the region that emitted it is now tens of billions of light-years away. But the walkway has an important limitation. It stretches inside a larger room. Cosmic expansion does not require space to stretch into an external room. The changing distance is part of the geometry of space itself. This leaves us with several different meanings of distance, each answering a different question. Look-back time describes how long the observed light has been travelling, and therefore how far into the past we are seeing. Light travel distance expresses that duration in light-years, which is useful as long as we remember that it is not necessarily the source's current separation from us. Proper distance describes the separation between two locations at a chosen cosmic time according to the cosmological model being used. Because the universe evolves, that distance can change from one cosmic time to another. Co-moving distance uses coordinates designed to remain attached to the average cosmic expansion. A galaxy participating in that expansion can keep roughly the same co-moving coordinate even while its proper distance increases. The terminology may sound like an unusually ambitious filing system, but each label prevents us from quietly replacing one question with another. How old is the light? How far away was the source when the light was emitted? How far away would that region be measured today? These are related questions, not identical ones. The cosmic microwave background makes the distinction especially clear. Its photons began traveling freely when the universe was about 380,000 years old. At that time, the matter from which the photons last scattered was far closer to the region that would become our location than it is today. During the long journey of the radiation, cosmic expansion increased the large-scale separation. We now receive the ancient photons after a travel time of almost 13.8 billion years, but under the standard model, the regions associated with that earliest visible light are presently much farther away than 13.8 billion light-years. We cannot directly see those regions as they are today. Any light showing their later condition is still somewhere along its journey, assuming it can ultimately reach us at all. Their present distance is therefore inferred from measurements and a model of the universe's expansion history. We observe the old message. Cosmology reconstructs the changing route. It may seem that expansion should prevent the photon from reaching us, as though space were carrying its destination away faster than the photon could approach. At some stages of a very long journey, the proper distance between the photon and us can indeed increase even though the photon is locally moving in our direction. This does not mean the light has turned around. It means the expanding separation is temporarily growing faster than the photon reduces it. As the expansion rate and the relevant cosmic scales evolve, that same photon may later enter a region where it can make net progress toward us. The full path can therefore be more subtle than a beam moving across a fixed diagram. This is also why distant galaxies may have cosmological recession rates greater than the speed of light, without locally racing past nearby objects faster than light. Special relativity still governs local measurements. The faster-than-light recession arises from the evolving geometry used to describe separation across enormous distances, so the visible universe is larger than a simple multiplication of its age by the speed of light, because the ruler has not remained fixed during the measurement. The older signals crossed a universe whose scale changed around them, and their sources continued to be carried into greater separation while the signals moved toward us. The approximate 46 billion light-year radius is not measured by sending a tape into space. It is calculated from the expansion history supported by cosmological observations, including the microwave background and the large-scale behavior of galaxies. Change the model or its measured parameters, and the precise result changes slightly. The essential lesson remains. Travel time measures the age of the message. Present cosmic distance describes the universe after expansion has continued throughout that journey. Once we keep those ideas separate, the contradiction fades, and a new boundary comes into view: the greatest present distance from which any information has had time to reach us. This is the particle horizon. The particle horizon is the farthest boundary of our present cosmic history. It does not mark the final location of matter, the outer surface of space, or the place where the universe has been physically cut off. Instead, it separates events whose signals could have reached us by now from events whose signals have not had enough time to arrive. To define it, cosmologists imagine tracing every possible light path backward from our present location through the entire expansion history of the universe. Some paths begin nearby and only recently. Others stretch across billions of years, passing through a cosmos whose scale changed continuously around them. The longest possible paths define the particle horizon. Anything inside that horizon may in principle have influenced what we observe today. Anything beyond it could not yet have sent information to us, even if stars, galaxies, or entire regions of space exist there. The boundary is therefore made not from matter, but from causality. It is the limit of our accumulated cosmic conversation. The word particle can make the idea sound as though a layer of tiny objects surrounds the visible universe, but that is not what the name means. It refers to the maximum distance from which a particle or signal moving at the speed of light could have reached an observer since the earlier stages of cosmic history. Imagine messages being sent toward us from every possible distance. A message from the moon has had more than enough time to arrive. A message from Andromeda has also arrived, although it began travelling millions of years ago. Signals from far more distant galaxies have crossed billions of years of changing space. Eventually, however, we reach regions so remote that even a signal sent as early as physically possible would not yet be here. The particle horizon lies at that divide. It resembles the outer limit of a delivery network whose roads have been stretching throughout the journey, and whose opening time was set by the beginning of the universe's observable history. No message beyond the boundary has reached our address. That does not mean there is no sender. This horizon should not be confused with the cosmic microwave background. The microwave background is the oldest electromagnetic light we can directly observe, because the earlier universe was opaque. The particle horizon is more fundamental. It describes the greatest causal reach available over cosmic time, whether or not ordinary light could travel freely during every part of that history. The surface of last scattering is therefore an observational screen produced by the early plasma, while the particle horizon is a limit determined by space-time and elapsed cosmic history. They appear close together in many simplified pictures because both concern extremely early signals, but they answer different questions. One tells us how far back electromagnetic vision can penetrate. The other tells us how far any influence could have travelled to us under the model. A fog may prevent you from seeing a distant landscape even when sounds or vibrations could carry through it. In the early universe, other physical traces may preserve indirect information from before light began travelling freely, though recovering such evidence is extraordinarily difficult. The particle horizon also explains why the observable universe appears centred on us, without placing us at a privileged centre. From Earth, the maximum region capable of influencing our present surrounds Earth because Earth is where the observations are being collected. If we move to a distant galaxy, the particle horizon would be centered on that new observer instead. Much of its observable region might overlap with ours, but not all of it. The distant observer could receive signals from places that remain beyond our current horizon, while some regions visible from Earth might lie beyond theirs. Imagine several people standing far apart across an enormous plain during a misty morning. Each person occupies the center of a different visible circle. Their circles overlap, but none of them marks the center of the entire landscape. The analogy helps. Although cosmic horizons are not caused by ordinary mist, they arise because signals have finite travel time, and the universe has a finite observed history. Every observer stands at the center of their own evidence, not necessarily at the center of existence. As cosmic time passes, the particle horizon changes. New signals continue arriving from regions whose earlier messages had not yet reached us. In that sense, the observable history available to future astronomers can contain information unavailable today. Yet the newly received light will not show those distant regions in a shared universal present. It will reveal them at the earlier times when their signals began travelling. And cosmic expansion complicates the picture further. The present-day distance assigned to the particle horizon depends on the expansion history reconstructed from observations and on the cosmological model used to interpret them. This is why its approximate radius is much greater than the simple age of the universe expressed in light years. The boundary cannot be marked by a stationary buoy in space. Its distance, meaning, and relation to visible objects evolve with cosmic time. A neat diagram may draw it as one clean circle, but the universe has once again declined to provide an actual line for us to follow. So where are we now? We have travelled beyond the oldest freely moving electromagnetic light and reached a concept rather than a place. The particle horizon tells us the greatest region that could have contributed information to our present moment. Inside it lies everything currently observable in principle, including ancient radiation galaxies at many stages of development, and all the nearby structures of our more recent cosmic surroundings. Beyond it may lie more universe, but no signal from those regions has yet joined our history. The particle horizon does not answer whether the entire universe is finite, infinite, curved, or connected in some larger pattern. It only tells us where present observation must stop, and because another observer would draw a different horizon around themselves, the next step in our journey is to leave Earth's apparent central position behind and ask how every observer can seem to occupy the middle of the visible universe. Every observer appears to stand at the center of the visible universe. From Earth, galaxies surround us in all directions. The cosmic microwave background forms an ancient glow across the entire sky, and the particle horizon can be pictured as a vast sphere centered on our location. Taken too literally, this image seems to return humanity to an old and flattering idea. Perhaps Earth occupies the middle of everything. But the apparent center belongs to observation, not necessarily to space itself. We are at the center of the region whose light is reaching us now for the simple reason that we are the ones receiving it. Every path in our past light cone ends here at this place and this moment. Move the observer, and the paths end somewhere else. The observable universe is centered on whoever is doing the observing. That fact makes our position important to our measurements, but it does not make Earth a throne around which the cosmos has been arranged. Imagine an astronomer living in a galaxy several billion light-years from the Milky Way. Their sky would contain a cosmic horizon centered on their galaxy, not ours. Some of the universe visible to them would overlap with the region visible from Earth. We might observe many of the same ancient structures from different directions and at different stages of their histories, but their observable sphere would also include regions whose signals have not yet reached us, while portions of our visible universe might lie beyond their own particle horizon. Neither observer would possess the complete map. Each would receive a different collection of cosmic messages determined by location time and the paths information had been able to travel. Picture two lamps glowing inside a vast mist. Each lamp illuminates a sphere around itself. The spheres may overlap, but neither sphere defines the full extent of the mist. The analogy is not exact, because cosmic horizons are not produced by lamps or ordinary fog. Still, it reminds us that a limit centered on an observer need not be a boundary centered on the entire universe. The distant astronomer would also see the Milky Way in the past. If their galaxy lay 2 billion light-years from us, the light reaching them from our region would show the Milky Way as it appeared roughly 2 billion years earlier, with additional cosmological details depending on the expansion between us. They could not look through a telescope and see Earth tonight. Our present light would not yet be there. In the same way, we cannot see their galaxy as it exists at this moment according to any simple universal clock. We see an earlier version carried by the light arriving now. Each observer looks outward into a personal arrangement of past events. Their present skies differ because their histories of received information differ. There is no single cosmic balcony from which every object can be viewed simultaneously as it is right now. Relativity and cosmic distance do not provide the universe with one universally accessible present. They provide local moments connected or not yet connected by signals. Why then does the universe look broadly similar in every direction from Earth? On small scales, it does not. One direction may contain the bright disk of the Milky Way. Another may point through thinner galactic dust. Galaxies gather into groups and clusters, while enormous voids contain far less matter. The local universe is lumpy structured and not especially committed to visual symmetry. But when astronomers examine sufficiently large scales, the distribution of matter becomes statistically more uniform. No direction appears to contain a confirmed outer edge, a unique wall, or a special concentration marking the center of all space. This broad assumption is called the cosmological principle. At very large scales, the universe is approximately homogeneous and isotropic. Homogeneous means that no sufficiently large region is expected to be fundamentally privileged over another. Isotropic means that the universe has broadly similar statistical properties in different directions. These ideas are supported within the observable region, though we cannot test them directly across the entire universe beyond our horizon. A useful comparison is the surface of Earth considered only as a two-dimensional world. A traveller standing in Bangkok can draw circles of increasing distance around Bangkok. Someone in Nairobi can do the same around Nairobi. Each city becomes the centre of its own map, yet neither city is the centre of Earth's surface. In fact, the surface has no special central point located somewhere upon it. Its geometric centre lies in a different dimension inside the planet, but that external viewpoint is not necessary for travellers living on the surface to describe their world. The analogy should not be pushed too far. The universe is not simply the surface of a larger cosmic ball, and current cosmology does not require an external space into which our universe is embedded. Still, the comparison shows how many observers can each occupy the centre of a coordinate system without any of them occupying a unique centre of the whole. Coordinates are allowed to be helpful without being royal. If our imaginary traveller departed Earth and crossed an enormous distance, they could not approach the edge of our observable sphere like a spacecraft approaching the surface of a planet. Their own observable region would gradually change. New light paths would end at their new location. Some regions would become easier to receive signals from, while others would recede into a different causal relationship. The traveller would carry the centre of observation with them, not because the universe follows the spacecraft, but because observation is always organised around the event where information arrives. The supposed edge would refuse to remain a fixed destination. It would be redrawn by the traveller's movement, by the passing of cosmic time, and by the continuing expansion of space. We have therefore removed another imagined wall. The observable universe surrounds us, yet it is not built around us. And if the horizon changes with the observer, we must now ask whether any traveller, no matter how patient or fast, could ever reach it at all. The horizon cannot be approached like a destination marked on a map. If our imaginary spacecraft turned away from Earth and accelerated into deep space, the boundary of the observable universe would not remain fixed ahead of it waiting to be crossed. The traveller would carry a new point of observation along the route. Light would continue arriving from different directions, cosmic time would continue passing, and the region capable of influencing the spacecraft would gradually differ from the region visible from Earth. This is the central difficulty. The particle horizon is not an object occupying one distant address. It describes the boundary of a past light cone at a particular place and moment. Change the place, change the moment, and the observable region changes as well. A navigator could enter coordinates for a galaxy, a cluster, or even an enormous empty region between filaments. The universe has been less generous with coordinates for the edge. The familiar analogy is a traveller chasing the horizon across an open landscape. Walk toward the distant line where the ground seems to meet the sky, and the line retreats. You can reach the hill tree or building that once appeared near it, but upon arriving a new horizon surrounds you. The cosmic version shares this failure to arrive, though for a deeper reason. A landscape horizon moves because your viewpoint changes across a curved surface. The cosmological horizon changes because your location in space-time changes, because signals require time to travel, and because the universe evolves while you move. Even a spacecraft travelling for billions of years would not find a thin, glowing shell labelled observable universe. It might reach regions that Earth currently observes only in their distant past, but from the spacecraft's perspective, those regions would become local surroundings. While a new and different cosmic history opened around them, speed does not solve the problem. A spacecraft with mass can be accelerated closer and closer to the speed of light, but never through it. As its speed increases, the energy required for further acceleration grows without providing a final step beyond the limit. This does not mean a fast traveller experiences distance exactly as an observer remaining on Earth would. Relativity changes the relationship between elapsed time-measured distance and simultaneity for observers in different states of motion. A sufficiently rapid journey could feel shorter to those on board than it appears from Earth. Yet no amount of ordinary acceleration allows the traveller to outrun light locally, or escape the causal structure that defines which events can reach them. The horizon is created from that same structure. Trying to defeat it by moving nearly as fast as light is rather like trying to outrun the rules used to describe the race. Admirable enthusiasm perhaps, but not a particularly promising transport plan. Suppose the traveller chooses a galaxy presently observed near the outer reaches of our visible history. What we see from Earth is ancient light emitted when that galaxy was much younger. During the billions of years since the light began travelling, the galaxy's present-day region may have become vastly more distant through cosmic expansion. The traveller cannot simply aim at the image as though it marks the galaxy's current location. They must account for how the separation evolves while the spacecraft moves. Depending on the distance and the future expansion of the universe, some destinations may be reachable in principle, while others may never be reached by any signal we send now. Their light can arrive here because it began its journey under earlier cosmic conditions, even though a message departing from Earth today may not be able to complete the reverse journey. Cosmic communication is not always a symmetrical exchange. We can receive an old letter from a region to which no reply will ever be delivered. This may sound as though these distant galaxies crossed a forbidden speed limit, but cosmological recession is not the same as an object locally rushing through nearby space faster than light. On sufficiently large scales, the distance between widely separated unbound regions can increase so rapidly that their recession rate defined through the cosmic expansion exceeds the speed of light. Relativity forbids an object from overtaking a neighbouring beam of light in a local measurement. It does not require the evolving distance between remote regions of expanding space to behave like the speed of an ordinary vehicle. A photon can always move locally at light speed toward us, while its proper distance from us temporarily increases because the intervening cosmic separation is growing even faster. Under the right expansion history, the photon may later begin making net progress and eventually arrive. This is one reason a simple circle labelled faster than light cannot serve as an absolute edge. The traveller would therefore encounter no moment when the stars suddenly stopped and a final darkness began. Regions once seen from Earth as ancient would become closer and more recent from the traveller's new viewpoint. Other regions would slip into a different relationship with the spacecraft's past and future. the observable universe would be redrawn continuously, not as a material sphere carried through space, but as a changing set of events able to exchange information with the traveller. And here our language needs greater care because several different boundaries are often called cosmic horizons. One describes how far signals have reached us so far. Another marks a present relationship between expansion and distance. A third concerns which signals may ever reach us, even given unlimited future time. They can lie at different distances, evolve in different ways, and answer very different questions. Before we travel farther, we must separate these three horizons and allow each one to keep its own meaning. The universe has more than one horizon, which is inconvenient only because we gave several different ideas almost the same name. A diagram may show three circles surrounding an observer: the particle horizon, the Hubble sphere, and the cosmic event horizon. They can look like variations of one boundary, yet each answers a different question. The particle horizon asks how far information could have travelled to us over the history of the universe. The Hubble sphere describes a present relationship between distance and cosmic expansion. The event horizon asks which events may ever be able to influence us, even if we wait through the entire future. One concerns the past, one concerns the current expansion rate, and one concerns the ultimate reach of future communication. Keeping those directions in time separate is the simplest way to avoid confusion. They are not three walls nested around Earth. They are three limits produced by different parts of the universe's causal history. We have already met the particle horizon. It surrounds the region from which a signal could have reached our location by the present cosmic time. To find it, cosmologists trace possible light paths backward through the changing expansion of the universe. Nearby signals needed only a small part of cosmic history to arrive. The most distant possible signals required nearly all of it. Beyond the particle horizon are events that have not yet had enough time to influence us. This boundary grows as the universe ages because additional signals continue joining our observable history. It is therefore a record of what could have reached us so far, not a prediction of everything we will ever see. Imagine a postal map shaded to show every place from which at least one message could have arrived before tonight. The shaded region describes the history of received communication. It says nothing by itself about whether tomorrow's mail can come from farther away, or whether a reply sent tonight could ever return. The Hubble sphere answers a different question. At any chosen cosmic time, astronomers can use the Hubble expansion rate to identify a distance at which the recession rate associated with the average expansion equals the speed of light. That distance is often called the Hubble radius, and the sphere centered on an observer at that radius is called the Hubble sphere. Galaxies beyond it can have recession rates greater than light speed because the large-scale separation between us is increasing through cosmic expansion. They are not locally rushing past nearby objects faster than a beam of light. This distinction matters. Relativity limits the speed measured for objects and signals passing one another locally. It does not require a vast evolving distance across curved space-time to behave like the speedometer of a spacecraft. The Hubble sphere marks where a particular recession rate condition is satisfied at one cosmic time. It is not automatically the edge of visibility, and it is not a forbidden surface. In fact, we can observe light that was emitted by galaxies beyond the Hubble sphere. This seems impossible only if the sphere is treated as a permanent wall. A photon may begin its journey toward us, while its proper distance is still increasing, because the space between its location and ours is expanding more rapidly than the photon can initially reduce that separation. The photon is always moving locally toward us at light speed, but the changing cosmic distance can temporarily carry it farther away. As the expansion history evolves, the Hubble sphere may change and the photon may eventually enter a region where its distance from us begins to decrease. After a sufficiently long journey it arrives. The result is subtle but important. Faster-than-light recession does not automatically make an object invisible, and crossing the Hubble sphere does not resemble crossing an event horizon. A photon can pass from one side of the Hubble sphere to the other. The boundary belongs to the cosmic rate at that time, not to a permanent division between knowable and unknowable space. The cosmic event horizon is the most future-facing of the three. It separates events that may eventually send us a signal from events whose signals will never reach us even if the future continues indefinitely. Its existence and location depend on the entire future expansion history of the universe. In a universe whose accelerated expansion continues broadly as described by the current standard model, there are distant regions from which light emitted sufficiently late will never arrive here. Space between us and those regions will grow in such a way that the signal cannot overcome the increasing separation. Yet we may still see ancient light from galaxies now associated with regions beyond that future communication boundary. Their older photons began travelling when cosmic conditions were different. We can receive their history while being unable to receive their endlessly continuing future. The universe permits the arrival of an old message without promising that another message can follow forever. A map may help keep the three ideas quiet and orderly. The particle horizon marks where messages could have reached us by now. The Hubble sphere marks where the present recession rate equals the speed of light. The event horizon marks the boundary beyond which some future messages can never reach us, assuming a particular future history of expansion. These circles need not coincide, and they evolve for different reasons. Only the particle horizon directly defines the broad causal extent of what is observable at the present time. The Hubble sphere is not a true one-way boundary. The event horizon concerns infinite future accessibility and depends on what dark energy and cosmic expansion eventually do. None of them is the physical edge of the universe. All three describe relationships among distance, light time, and expansion. And to understand why expansion can create such unusual relationships without carrying galaxies through an external emptiness, we must now examine what it means for space itself to expand. Expansion, without an outside, is one of those ideas that sounds impossible, mainly because every familiar example expands into something else. A balloon grows into the room around it. Smoke spreads through the air. A drop of ink widens through water. Our experience teaches us that expansion means an object occupying more of a surrounding space. But when cosmologists say the universe is expanding, they are not describing galaxies rushing outward into a larger empty container. They are describing a change in the measured distances between widely separated gravitationally unbound regions. The geometry of space evolves, and the scale connecting distant locations grows with time. There is no confirmed central point from which everything was launched, and the standard cosmological description does not require an external emptiness waiting beyond the universe. The universe is not expanding toward a destination. On sufficiently large scales, the distances within it are changing. Imagine a faint grid drawn through intergalactic space with galaxies resting at widely separated points. As cosmic time passes, the grid lines spread farther apart. A galaxy that follows the average expansion may remain at roughly the same moving coordinate, meaning it keeps its place relative to this expanding pattern, while its proper distance from other remote galaxies increases. The galaxy does not need to fire engines or move locally through its surrounding space at an extraordinary speed. Instead, the large-scale measure of separation changes between the regions. This picture helps, but the grid is not a physical substance hiding between galaxies. There are no elastic threads stretching through the void, no machinery pulling one cluster away from another, and no small labels attached to space-time explaining which section is scheduled to expand next. The grid is a mathematical way of tracking how distance behaves in the cosmological model, useful, quiet, and fortunately free of maintenance costs. The expansion also does not enlarge everything equally. Your room is not slowly becoming wider because of the Hubble expansion. Earth is not being stretched away from the Moon in the same simple manner, and the solar system does not expand along with the average distance between remote galaxies. Local forces matter. Atoms are held together by electromagnetic interactions. Planets and stars are bound by gravity. Galaxies and galaxy groups may remain gravitationally connected even while the much larger universe expands around them. Cosmic expansion becomes dominant only across sufficiently large distances where matter is not strongly bound into one system. A coin placed on a table does not grow because the universe grows. Nor does the table, which will no doubt be relieved to learn that cosmology has assigned it no additional responsibilities. Expansion describes the large-scale behavior of the universe, not a universal stretching imposed identically on every object. One common illustration uses dots drawn on the surface of an inflating balloon. As the balloon expands, every dot becomes farther from most other dots, and no dot on the surface serves as the center of the expansion. From the viewpoint of a creature able to live only on that two-dimensional surface, the distances within its world increase without requiring a special central location on the surface itself. This captures two useful ideas. Expansion can occur everywhere, and every observer may see distant regions receding without occupying the center of the whole. But the analogy can also mislead. A real balloon expands into the room, has a rubber surface, and possesses a three-dimensional center outside the two-dimensional world of the dots. Our universe has three spatial dimensions, and cosmology does not require it to be the boundary of a higher dimensional ball. The balloon's surrounding room belongs to the analogy, not to the scientific claim. Another familiar picture replaces the balloon with rising bread filled with raisins. As the dough expands, the average distances between raisins increase. Each raisin sees distant raisins moving away, and more distant ones separate more rapidly because more expanding dough lies between them. This resembles the large-scale relationship described by Hubble's law. Yet galaxies are not raisins, space is not dough, and the universe is not resting in a cosmic oven whose timer was set 13 billion years ago. The value of the analogy lies only in the changing separation. It also helps explain cosmological redshift. As light travels through expanding space, its wavelength is stretched along with the evolving cosmic scale. Light emitted at shorter wavelengths can arrive at longer, redder wavelengths after a long journey. For the oldest visible radiation, the stretching has been so great that light once released at much shorter wavelengths now reaches us as microwaves. The Big Bang is often imagined as an explosion from one point into surrounding darkness, but that picture places the event inside a space that already exists. In the Standard Model, the early hot dense state was not concentrated at one location in present-day space. It described the universe everywhere within the region we can trace backward. Every sufficiently large region was once hotter and denser, and expansion increased the scale between regions over time. Asking where the Big Bang happened is therefore not like asking where a firework exploded. From our current perspective, it happened here in the region that became the Milky Way, and also in every other region whose history can be traced back to that early state. There is no surviving blast center around which galaxies form a growing shell. The expansion has no known spatial middle, just as it has no observed outer wall. Once this is understood, an edge becomes even less necessary. Space can expand without moving into anything because expansion describes relationships within space rather than motion toward an exterior. Yet this still does not tell us whether the complete universe is infinite. An infinite universe can expand as distances between its regions grow while remaining infinite. A finite universe may also expand without developing a boundary, depending on its geometry and global connectivity. The difference between finite and infinite is therefore not the same as the difference between edged and edgeless. We have removed the imagined container, the explosion center, and the external emptiness. What remains is a quieter geometric question. Can the universe have a limited total size while allowing a traveller to continue forever without meeting a wall? A universe can be finite without possessing an edge. The idea feels contradictory because most finite objects in ordinary life have boundaries. A table has sides. A field has a fence or a shoreline. A sheet of paper ends where the paper stops. Yet geometry allows spaces with a limited total size and no final border anywhere within them. A traveller could continue moving without encountering a wall, a cliff, or a point where distance ceased to exist. Depending on the shape and connectivity of space, the path might eventually return to its starting region, perhaps from a direction that once seemed impossibly far away. This possibility does not mean our universe is known to behave that way. It means the words finite and edge describe different properties. Finite concerns total extent or volume. Edge concerns the presence of a boundary. The universe might be infinite and unbounded or finite and unbounded. The absence of a wall does not decide between them. The familiar example is the surface of Earth. Consider only the two-dimensional surface, ignoring the air above it and the interior below. Its area is finite, yet a traveller can move across it without reaching an edge. Walk far enough in one direction, and the path may eventually return to its starting point. No border of the surface must be crossed. This helps us imagine finite but unbounded space, although the universe is not simply a larger version of Earth's surface. Earth's surface has two dimensions and curves through a third dimension that we can easily picture. Cosmic space has three dimensions, and its curvature can be described from measurements made within it, without requiring us to imagine it bending into an external room. A positively curved three-dimensional universe could in principle possess finite volume without a boundary. The mathematics is sound. Whether the real universe has that global form is another question entirely. To explore that question, we must separate geometry from topology. Geometry describes local properties such as curvature distances and the behavior of angles. Topology describes the larger pattern of connection, whether space continues endlessly, closes around itself, or joins distant regions through repeated identifications. Two spaces can share the same local geometry while possessing different global topologies. A flat tabletop and the surface of a cylinder are locally similar in the sense that small regions can appear flat, yet their overall connections differ. Roll a sheet of paper into a cylinder, and one direction loops while another remains open. Join more directions in a mathematical construction, and a flat space can become finite and connected back upon itself. There is no need to picture an actual folded sheet floating in a higher dimensional workshop. The folding is only a visual aid for relationships between locations. Cosmic topology concerns how space connects internally, not how it might look from an imaginary viewpoint outside the universe. Observations indicate that the spatial geometry of the observable universe is very close to flat on large scales. In plain language, the cosmic triangles and distance relationships we can measure do not reveal strong overall curvature across the region available to us. But near flatness does not prove that the entire universe is infinite. A vast curved surface can look almost flat when only a small patch is visible. Earth appears flat across a quiet field because the field is tiny compared with a planet. Likewise, our observable region could be only a small portion of a much larger curved universe, and even a perfectly flat universe could be either infinite or compact depending on its topology. Geometry tells us how space behaves nearby. It may not reveal how all of space connects beyond the horizon. The cosmos can therefore pass every local flatness test while still keeping its global arrangement carefully out of sight. If space wrapped around itself on a scale small enough to observe light, might travel along more than one route and show us repeated images of the same distant structures. We might see one galaxy in several directions, each image arriving after a different journey. Patterns in the cosmic microwave background could also repeat, producing matching circles or related features across widely separated parts of the sky. Astronomers have searched for such signatures, but no convincing evidence of a compact repeating topology has been found on the scales tested. This does not prove that space never loops. The repeating scale may be larger than the observable universe, the topology may be more complicated than the tested forms, or the signatures may be too subtle to identify. A wrapped universe larger than our horizon could appear indistinguishable from an infinite one within everything we can currently observe. The most important sections of the cosmic map may lie beyond the only page we've been given. Suppose our imaginary traveller continued forward through such a universe. In an infinite cosmos, the path might extend without end, always entering new regions and never returning. In a finite connected cosmos, the traveller might eventually approach the starting region from another direction, though cosmic expansion travel time limits and the changing universe would make the journey far more complicated than circling Earth. In neither case must there be a wall, and from our present position, we cannot determine which possibility describes the complete universe with confidence. We know that the observable region extends enormously beyond our galaxy and appears close to spatially flat. Evidence suggests that space probably continues beyond our particle horizon, but the total size and global topology remain unknown. We have reached the point where geometry offers several valid universes, while observation has shown us only one limited region. So the next question is no longer whether a wall waits at the edge. It is what science can responsibly say about the space that may continue beyond the reach of our oldest light. Beyond the region our light can reach, the universe does not suddenly become empty. Nor does it become a blank page on which science is free to write anything it likes. The honest answer is quieter. We cannot directly observe beyond our particle horizon, because no signal from those regions has had enough time to arrive here. That limit prevents photographs, measurements, and messages from crossing into our present evidence. Yet it does not necessarily mark the end of space. The galaxies closest to the horizon do not appear arranged against a wall, and the large-scale patterns we observe do not show a confirmed outer boundary approaching in any direction. Instead, the visible universe remains broadly continuous as far as our observations extend. The simplest interpretation is that space and matter probably continue beyond the region available to us. But probable continuation is not the same as direct detection. At the horizon, astronomy changes from seeing what is there to asking what the observed universe allows us to infer. One reason cosmologists expect some continuation is the broad uniformity of the observable universe. On smaller scales, matter is gathered unevenly into stars, galaxies, clusters, filaments, and enormous voids. But across sufficiently large regions, no observed direction appears to contain the unique edge center, or fundamentally different half of the cosmos. The cosmic microwave background is also remarkably uniform across the sky, with tiny variations carrying the seeds of later structure. This supports models in which the observable region is one part of a larger, broadly similar cosmic domain. Cosmologists often describe that expectation through the cosmological principle On very large scales, the universe is treated as approximately homogeneous and isotropic. The principle has been highly useful within the region we can test. Extending it beyond the horizon is reasonable, but it remains an extension. We cannot place a telescope outside the observable universe to check whether the same pattern continues indefinitely. Cosmic inflation provides another reason to suspect that the complete universe is much larger than the region visible today. In many inflationary models, the very early universe experienced an extremely brief period of rapid expansion. A tiny region was stretched to an enormous scale, smoothing its large-scale geometry, while carrying small quantum variations outward. Those variations later help provide the starting pattern from which galaxies and cosmic structure developed. Inflation can help explain why widely separated parts of the observable universe possess similar overall conditions, even though without an earlier connecting process they would appear never to have exchanged enough information. It can also help explain why the observable region appears so close to spatially flat. Yet inflation is not one single completed theory with every detail established. Many versions exist, and the physical mechanism that drove it has not been directly identified. The evidence supports important features associated with inflationary thinking, but it does not provide a map of whatever lies beyond our horizon. Imagine hearing a long piece of music through the wall of a neighboring room. You can hear several minutes clearly. The melody follows patterns, the rhythm continues smoothly, and nothing near the end of the audible passage suggests that the composition suddenly stops. It would be reasonable to suspect that the music continues beyond what you can hear. You might even infer that the unheard section follows related musical rules, but you could not know the next note the total length, or whether the composition eventually changes. The universe beyond the horizon is similar only in that limited sense. The observable region supplies evidence of continuity and regularity. Our physical models extend those patterns farther. But the wall in this analogy is not a physical cosmic barrier, and the unheard music is not secretly leaking through. Regions beyond the particle horizon have sent us no direct information. Their contents cannot be reconstructed in detail merely because the visible portion appears orderly. Could the unseen universe contain galaxies much like those around us? Quite possibly. Could it contain structures arranged from the same kinds of matter and governed by the same physical laws? Standard cosmological models generally assume so, at least across a much larger domain than we observe. But we cannot responsibly claim that every inaccessible region must be identical to ours. We do not know the total size of space, its complete topology, or whether conditions remain uniform across arbitrarily great distances. Ideas involving distant domains with different histories or physical properties appear in some theoretical models, but these possibilities move farther from established observation. The word possible is generous. It describes what a model may allow, not what nature has confirmed. Beyond the horizon, there may be more of the familiar universe, an unimaginably extended variation of the same cosmic web, or global features our observable region is too small to reveal. Science can compare such possibilities, but it cannot quietly promote one into a discovered landscape. The horizon itself also changes with time. As the universe ages, light from somewhat more distant events can enter our particle horizon, adding new information to the observable record. Future astronomers may therefore receive signals that have not reached us yet. But accelerated expansion introduces a second limit. If the large-scale expansion continues broadly according to the current standard model, some remote regions will remain permanently unable to send us newly emitted signals, even given unlimited future time. We may see their ancient light while never seeing their later history. This means the universe can reveal more of its past while closing access to parts of its future. The result is not a clean outward frontier advancing through static space. It is an evolving pattern of causal connection. Some messages are still arriving. Some have not arrived yet. Some may never arrive at all. The cosmos keeps no simple border ledger, so what lies beyond the region our light can reach? The most responsible answer is that the universe probably continues, but observation cannot tell us its detailed contents. Inflationary models and the large-scale regularity of the visible cosmos provide reasons to expect a far greater domain beyond our horizon. They do not reveal whether the complete universe is finite, infinite repeating, or globally unlike the portion around us. We have followed the evidence as far as signals allow, and here the journey encounters its deepest boundary. Not a wall, not a final galaxy, not a darkness proven to contain nothing. We have reached the place where the word discover reaches its own limit. One final step remains to gather the horizons, ancient light expanding distances and unanswered geometry into the clearest answer we can give before allowing the journey to return quietly home. At the quietest limit of our journey there is no wall waiting for us. No final galaxy hangs beside a border, and no spacecraft reaches a place where space suddenly ends. The edge we have been approaching is not a physical surface. It is an observational horizon shaped by the finite age of the universe, the finite speed of information, and the expansion of space during the long journey of light. Everything within our particle horizon belongs in principle to the history that could have influenced us by now. Beyond it may lie more space, more matter, and more cosmic history, but no signal from those regions has yet reached our present location. So the clearest answer to our original question is this: if you tried to reach the edge of the universe, you would not find a stationary destination. Your own horizon would change as you travelled, while the supposed boundary continued to describe the limits of your received information rather than the end of existence. We know that the universe has an observable history extending back to a hot, dense early state. We know that light takes time to travel, so distant objects appear as they were in the past. We know that the cosmic microwave background carries the oldest electromagnetic image presently available to us, released when the young universe became transparent. We also know that cosmic expansion has increased the present separation between us and the regions that emitted the most ancient light. These facts are supported by observations made across many wavelengths and by measurements of galaxies' radiation and large-scale structure. They allow cosmologists to construct a remarkably detailed history of the visible universe. Yet none of them reveals a physical outer wall. The surface of last scattering is not the end of space. The particle horizon is not a shell of matter. The Hubble sphere is not an uncrossable barrier, and the cosmic event horizon, if the future unfolds broadly as current models suggest, concerns future communication rather than the total extent of reality. Evidence suggests that the universe continues beyond what we can observe. The large-scale cosmos appears broadly uniform in every direction, without a visible edge approaching from one side. Inflationary models often describe a total cosmic domain vastly larger than our observable region. Measurements indicate that space is very close to flat across the portion available to us. All of this makes continuation a reasonable expectation. But expectation is not observation. We do not know whether the entire universe is finite or infinite. We do not know whether space eventually loops back upon itself, repeats through some larger topology, or extends without limit. We do not know whether regions far beyond the horizon remain exactly like our own cosmic neighborhood. They may follow the same broad physical patterns, but no telescope can bring us a direct picture from a place whose signals have not entered our causal history. Science reaches this boundary and does something valuable. It stops pretending certainty. That restraint does not make the answer empty. It gives the answer its proper shape. The horizon tells us that knowledge has a geography determined by causality. There are events close enough to influence us now, events whose information is still travelling, and events that may never become connected to our future. The universe is not divided into the real and the unreal at that boundary. It is divided into what has entered our evidence and what has not. A region beyond the horizon may be as physically real as the chair beside you, yet it cannot currently participate in any observation made here. This is a strange kind of distance. It is not merely a long journey through space, it is a separation in the possible exchange of information. We began tonight by searching for the place where the universe ends. What we found instead was the place where a particular observer's cosmic history becomes incomplete. Now imagine the journey reversing. The unresolved darkness beyond the horizon remains where it is neither confirmed empty nor filled by our imagination. The oldest microwave light softens into the background. The first galaxies reappear, followed by the long filaments and quiet voids of the cosmic web. Galaxy clusters separate into smaller groups. The Milky Way becomes visible again as a wide disk of stars, dust and gas. Somewhere within one modest spiral region, the sun returns as a familiar point of light. The planets gather around it. Earth grows from a pale speck into a blue world, and the night side turns slowly beneath the stars. Nothing about this return makes the cosmos smaller. The observable universe remains immense, and the unanswered region beyond it remains beyond our reach. But scale no longer needs to feel like distance from home. Every photon arriving at Earth connects this small world to a different part of cosmic history. Perhaps there is still a window near you. Beyond it, the night sky looks much as it did before we began. A few stars may be visible, or perhaps clouds and city light hide them completely. Either way, ancient signals continue arriving above the roof, across the street, and through the quiet darkness outside. They do not bring us a picture of the entire universe. They bring fragments, a nearby star from years ago, a galaxy from millions of years ago, a faint background from almost the beginning of visible cosmic history. From those fragments, human beings have learned to measure expansion, reconstruct vanished eras, and identify the border of what can presently be known. Beyond that border, the universe may continue farther than any distance we can meaningfully imagine. It does not need to provide a wall. It does not need to reveal an outside. For tonight it is enough to know that the edge is not where existence ends. It is where the arriving light grows silent, the answer becomes gentle, and curiosity is allowed to rest.